Note that the nodes in the graph are given a label that is the same as the number assigned to the corresponding packet switch. A graph representation is useful in computing next hop forwarding because graph theory has been studied and efficient algorithms have been developed. A graph abstracts away details, allowing routing software to deal with the essence of the problem. A routing algorithm must identify a link when it computes next hop forwarding for a graph. The forwarding table for node 1 raises an important point. The forwarding table may contain many entries that point to the same next hop. An examination of the WAN reveals why all remote entries contain the same next hop. The packet switch has only one connection to the network. Therefore, all outgoing traffic must be sent across the same connection, with the exception for entry that corresponds to the node itself. All entries in node 1's forwarding table have a next hop that points to link from node 1 to node 3. In our trivial example, a list of duplicate entries in a forwarding table is short. Here is the graph and table listing the next hop for each packet switch to reach a specific destination. A large WAN may contain hundreds of duplicate entries, so most WAN systems include a mechanism used to eliminate common types of duplicate entries. Default route allows a single entry in a forwarding table to replace a long list of entries with the same next hop value. Only one default entry is allowed in a forwarding table, and the default route entry has lower priority than other entries. If the forwarding mechanism does not find an explicit entry for a given destination, it uses the default route. Default routing is optional, and a default entry is present only if more than one destination has the same next hop value. This table displays a forwarding table with duplicate entries removed. The forwarding table for node 3 does not contain a default route because each entry has a unique next hop. However, the forwarding table for node 1 benefits from a default route because all remote destinations have the same next hop. Compare the tables. The first table shows the forwarding table without a default route. Note how many fewer entries are required when a default route is included in the second table. Now let's cover the two basic approaches to construct forwarding tables, either static or dynamic. A static routing program computes and installs routes when a packet switch boots. The routes do not change except when manually reconfigured. A dynamic routing program builds an initial forwarding table when a switch boots, and then it alters the table as conditions in the network change. Each approach has advantages and disadvantages. The advantages of static routing are simplicity and low overhead, but it has inflexibility. Static routes cannot be changed quickly when communication is disrupted. Large networks are designed with redundant connections to handle occasional hardware failures, so most WANs use a form of dynamic routing. WANs need to perform distributed route computation. Instead of a centralized program computing all shortest paths, each packet switch must compute its own forwarding table locally. All packet switches must participate in distributed route computation. All routers in an autonomous system under the control of one entity must participate in the routing scheme. Each autonomous system is configured with the same routing protocols. There are two general forms: link state routing, LSR, which uses an algorithm, and distance vector routing, DVR, which uses another approach. Link state routing protocols such as Open Shortest Path First, OSPF, and Intermediate System, ISIS, create a topology of the network and place themselves at the root of the tree. Link state protocols implement an algorithm called the shortest path first to determine the path to a remote destination. Distance vector routing is sometimes referred to as routing by rumor, as most routers depend on hearsay information rather than on their personal knowledge of the topology network. Routing Information Protocol is a distance vector routing protocol. Link state routing is also known as shortest path first routing approach. The Dijkstra algorithm uses it to characterize the way it works to find the shortest paths. To use LSR, packet switches periodically send messages across the network that carry the status of a link. For example, packet switches 3 and 4 measure the link between them and send a status message, such as, "The link between 3 and 4 is up." Each status message is broadcast to all packet switches, and every packet switch collects incoming status messages and uses them to build a graph of the network. Recall, when we first discussed IP version 4 addressing, we said there were 5 classes, A through E, with A, B, C assigned to networks. And D is the range of addresses assigned for multicasting. An LSR algorithm can adapt to hardware failures. If a link between packet switches fails, the attached packet switches will detect the failure and broadcast a status message that specifies that the link is down. All packet switches that receive the broadcast will change their copy of the graph to reflect the change in the link status and recompute the shortest path. Similarly, when a link becomes available again, the packet switches connected to the link detect that it is working and start sending status messages that report its availability. As with LSR, each link in the network is assigned a weight. The distance to a destination between 2 packet switches is defined to be the sum of weights along the path between the 2. A weight can be as simple as how many hops to the destination. Like LSR, distance vector routing, or DVR, arranges for packet switches to exchange messages periodically. However, in DVR, a switch sends a complete list of destinations and the current cost of reaching each. When it sends a DVR message, a switch is sending a series of individual statements of the form, "I can reach destination X, and its current destination from me is Y." DVR sends only to neighbor routers. Changes made and sent to the next neighbor routers and sends complete forwarding table. DVR messages are not broadcast. Each switch periodically sends a DVR message to its neighbors. The messages contains pairs listing the destination and distance in the form, destination, distance. And each packet switch must keep a list of possible destinations along with the current distance to the destination and the next hop. The list of destinations and the next hop for each can be found in the forwarding table. DVR is often referred to as routing by rumor because information is passed from one neighbor to another. Routers using distance vector protocol do not have knowledge of the entire path to a destination. Instead, they use 2 methods. The first is direction, in which the router or exit interface a packet should be forwarded, and 2, the distance from its destination. Distance vector protocols are based on calculating the direction and distance to any link in any network. Direction usually means the next hop address in the exit interface. Distance is a measure of the cost to reach a certain node. The least cost route between any 2 nodes is the route with minimum distance. Each node maintains a vector table of minimum distance to every node. The cost of reaching a destination is calculated using various route metrics. RIP uses hop count of the destination, whereas IGRP takes into account other information such as node delay and available bandwidth. Updates are performed periodically in distance vector protocol, where all or part of a router's routing table is sent to all its neighbors that are configured to use the same distance vector routing protocol. RIP supports cross-platform distance vector routing, whereas IGRP is a Cisco's system proprietary distance vector routing protocol. Once a router has this information, it is able to amend its own routing table to reflect the changes and then inform its neighbors of the changes. This process has been described as routing by rumor. EGP and BGP are not pure distance vector routing protocols because distance vector protocol calculates routes based only on link costs, whereas BGP, for example, the local route preferred value takes priority over the link cost. When a message arrives at a switch from neighbor N, the switch examines each item in the message and changes its forwarding table if the neighbor has a shorter path to some destination than the path currently being used. For example, if neighbor N advertises a path to destination D as having cost 5, and the current path through neighbor K has cost 100, the current next hop for D will be replaced by N, and the cost to reach D will be 5 plus the cost to reach N. Once a graph has been created that corresponds to a network, software uses a method known as Dijkstra's algorithm to find the shortest path from a source node to each of the other nodes in the graph. A next hop forwarding table is constructed during the computation of shortest paths. The algorithm must run once for each node on the graph. In other words, to compute the forwarding table for packet switch P, the node that corresponds to P is designated as the source node and the algorithm is run. Dijkstra's algorithm is popular and can be used with various definitions of shortest path. In particular, the algorithm does not require edges in the graph to represent geographic distance. Instead, the algorithm allows each edge to be assigned a non-negative value called a weight. The algorithm defines the distance between two nodes to be the sum of the weights along a path between the nodes. The figure illustrates the concept of weights by showing an example graph with an integer weight assigned to each edge and a least weight path between two nodes in the graph. Because it uses weights on links when computing shortest paths, Dijkstra's algorithm can be used with measures other than geographic distance. In theory, either LSR or DVR routing will compute shortest paths, and each approach will eventually converge, meaning that the forwarding tables in all packet switches agree. However, problems do occur. For example, if LSR messages are lost, two packet switches can disagree about the shortest path. DVR problems can be more severe because a link failure can cause two or more packet switches to create a routing loop in which each packet switch thinks the next packet switch is the next set of the shortest path to a particular destination. As a result, a packet can circulate among the switches indefinitely. One of the primary reasons DVR protocols exhibit problems comes from backwash. In other words, a packet switch receives information that it is sent. For example, suppose a switch tells its neighbors, I can reach destination D at cost 3. If the connection leading to destination D fails, the switch will remove the entry for D from its forwarding table or mark the entry invalid. But the switch has told the neighbors that the route exists. Imagine that just after the link fails, one of the neighbors sends a DVR message that specifies I can reach destination D at cost 4. Unfortunately, the message is believed and a routing loop will be created. The time to live field is used to prevent packets in a routing loop to continue forever. IP version 4 header displays with the time to live field marked. Most practical routing mechanisms contain constraints and mechanisms to prevent problems like routing loops. For example, DBR schemes employ split horizon, which specifies that a switch does not send information back to its origin. Furthermore, most practical routing systems introduce different things that prevent the software from making many changes in a short time. However, in a large network where many links fail and recover frequently, routing problems do occur.